Picking up where we left off in the last video, we're going to talk about the energy of a pulse of a laser. So if you're unfamiliar with a laser, what a laser is a laser shoots very, very concentrated, so to speak, light. Concentrated is not the most technical way of putting it, but a laser pulse is a whole bunch of waves of light that are all what they call coherent. They're all in the same phase together. They're all in phase. It's very intense light, but it's made up of photons. And so what the question is asking us to determine is how many photons does this pulse of laser light have? The information that we're given is that the laser has a wavelength of 337 nanometers. Should be that. Just replace the nano with times 10 to the negative 9. And it has an energy of 3.83 millijoules, which I'm going to go ahead and replace with times 10 to the negative 3 joules, because times 10 to the negative 3 is equivalent to milli. That is the 1,000th of a joule. So this is the information we're given. We're asked to find how many photons are in that pulse of the laser light. Our key here is to remember from the previous video this equation, or conversely this one, which is the same equation just with the wavelength instead of frequency. This equation gives us the energy of one photon of light. So, if we can work out what the energy of a single photon is of this particular wavelength of light, because we know the energy of the entire pulse, we can use the energy per photon to work out how many individual photons there must have been. So, E is equal to Planck's constant times C over the wavelength. Again, that comes from back here. It's the same thing as this equation, just if you remember, C is equal to the wavelength times the frequency. So all we did was we just did some algebra to this. Divide both sides by the wavelength. So V, which is actually is nu, sorry, the frequency is equal to C over the wavelength, and so we're just plugging that in for the frequency here to get this. So we know all of this stuff. So Planck's constant is 6.626 times 10 to the negative 34 joules seconds. Speed of light is 3 times 10 to the 8 meters per second. And the wavelength of light is 337 times 10 to the negative 9 meters. Oh, really big numbers and really tiny numbers. And, oh, hold on. That should not be... where is that? Sorry. My mind is going crazy for a second. Yeah, it is negative 34. For some reason, for a second, I thought that it was positive 34, but no, that's way too big of a number. Sorry about that. Brain fart. Happens to everybody. So, really big numbers and really tiny numbers. If we do all the math here, 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 337 times 10 to the negative 9. That tells us that the energy of one photon is 5.8, well, see, with sig figs it'd be 5.90, but we'll go ahead and do a 5.9898 times 10 to the negative 19 joules per photon. And that unit just is inherent to the question here, the adding of the photon on at the end. I know there's no photons up here, but this is the energy per photon, and so we can go ahead and stick that on the end there. So it's the joules for every one photon. We know the entire pulse was was 3.83 times 10 to the negative third joules. And so if we just plug this in here, just like it's a conversion factor, we know that we have 5.895 times 10 to the negative 19 joules for every one photon. And so if we do that math, oops, I wrote the wrong number there. That should be 898, not 895. But everything else is correct. So 898 times 10 to the negative 19. Our little pulse of laser light had 6.49 times 10 to the 15 photons. That is a lot of photons. Alright, hopefully that made sense. If not, we can talk about it next time we meet. But for now, let's go ahead and move on to this question. It says to arrange the three types of electromagnetic radiation, visible light, X-rays, and microwaves, in order of increasing wavelength, frequency, and energy per photon. So we have wavelength, frequency, and energy. And then for each of these things, we are going to list visible light, X-rays, and microwaves. And we'll go ahead and say this is the low end and this is the high end here. So to figure this out, we are going to go back and look at that table from way back here. There it is. So the electromagnetic spectrum. And we'll go ahead and do wavelength first, and then we'll be able to work out everything else using the wavelength. So if memory serves, it was microwave, visible, and X-rays, I believe, were the three things we were going to list. And so if we look at the wavelength, wavelength increases as you go this direction. And so the thing with the longest wavelength out of those three would be microwaves. It has the highest wavelength. Visible light would be next, and then X-rays. So if we go all the way back, yeah, visible, X-ray, and microwave. Okay, so the lowest, the smallest wavelength was X-rays, and then there was visible, and then there was microwaves. So we're not going to go back to that image again because we can work out everything else from just this. So if X-rays have the smallest wavelength, given what we know about the relationship between wavelength and frequency, we can work out what will have the highest frequency. And if you remember, the relationship is that they are inversely proportional. So as one of them goes up, the other one goes down. So in the case here, what we're going to end up doing is just flipping the order from the first one. Because they're inversely proportional, whatever the order is for wavelength, it's going to be the opposite for the frequency. So microwaves have the smallest frequency, visible is in the middle, and X-rays have the largest frequency. And again, this is just because they are inversely proportional. When it comes to the energy, if we think back to how we know how to calculate energy, we use these equations to do that. And if you notice here, the energy and frequency are directly proportional, and energy and wavelength are inversely proportional. The higher the frequency, the greater the energy, and so energy is actually going to be the same as frequency. So we have microwave radiation is the least energetic, visible is more energetic than microwave, and X-rays are even higher in terms of their energy. Alright, so moving on to talk more about light and how it behaves, why it does the thing it does. We're going to ask ourselves a question: is light a wave or a particle? Because for the longest time, people thought it was a wave. And then our buddy Einstein came along and said, no, actually, light is also a particle. Light exists as photons. And so the question we need to ask ourselves is, which one is it? Is it a wave or is it a particle? Because those are two different things. There is not a wave particle. Like this is not a thing. Those are two different things, waves and particles. Strangely enough, though, the answer to the question, is light a wave or a particle, is yes. It is both, actually. But it is not both simultaneously. In some situations it is a wave, and in some situations it's a particle. In some situations it behaves like a wave, and in some situations it behaves like a particle. It all just depends. And actually, the same thing goes for matter. Everything, actually, in the universe sometimes behaves like a wave, sometimes behaves like a particle. Now, most of the things that we are used to interacting with, the wave nature is incredibly tiny. So tiny that it's imperceptible. But it is still there. It is kind of like the Gollum versus Smeagol. You know, sometimes it's Gollum and sometimes it's Smeagol. It just kind of depends. It's what we call particle-wave duality. Before we get into that really in depth, though, we need to talk a little bit more about light and a little bit more about how we came about discovering the energy of electrons. So I think we'll go ahead and pick up with this one in the next video, because it's going to take a little bit of time to go through this topic, and the video is already a little bit long at this point. So we will pick up here in the next one.